In this video, I want to talk about the binomial distribution. So the binomial distribution is the way that we're going to calculate the probability of something happening I times out of n trials. So like if we flip a coin 10 times, what's the chance that we get 5 heads? What's the chance we get 3 heads? What's the chance we get 7 heads? Or if there's a cross between 2 heterozygotes, and they have 10 offspring, what's the chance we get 1 or 2 or 3 individuals with the recessive phenotype? Okay, so let's get into how this is going to work. So we're going to start with the probability that if we do something once, that we get this outcome or that outcome. And what we're going to do it with is just daughters and sons. So we're going to assume the 50% chance on any for any offspring that we get a daughter versus a son. And so then we're going to ask what's the probability that we get a certain number of daughters or sons. So we can start out, excuse me, if we just have one offspring, then we can get a son, in which case we have 0 daughters, or we can get a daughter, in which case we have 1 daughter. And so the probabilities of this are just 1/2 and 1/2. Okay, easy enough. If we get to 2, well, now we have 4 different combinations. We could have a son and a son. And the probability of that is 1/2 times 1/2, so 1/4. Or we could get a son and then a daughter. The probability of that is 1/2 times 1/2, so 1/4. Or we could get a daughter and then a son. So all of these have, each one has probability of 1/4. And so if I ask you a question like, what's the chance that you get a son and then a daughter, you can tell me it's 1/4. But if I ask you, what's the chance, given that you have 2 offspring, that you have exactly 1 son and 1 daughter? Well, then we need to include this case plus this case, right? So the chance then that we get exactly 1 daughter is equal to 1/4, the probability that we get a son and then a daughter, plus 1/4, the probability we get a daughter and then a son. And so what we're looking at here, and as we go on, we're going to see, like if we look at it for 3. So here are our combinations for 3. And if I ask you what's the probability that you have 3 offspring and one of them is a daughter, then that would be 3 lines, 3 different possibilities, times the probability per line. So as we saw here, the probability for each line is the same. Here it's actually 1/8, because it's 1/2 times 1/2 times 1/2. So it would be 1/8 the probability per line times the number of lines. And so generally we can write this as a probability for each line times the number of lines. That's going to be our general probability. And so we just need to figure out these 2 things. So we've already we're close to the probability for each line. We saw here it was 1/2, just 1/2 once. And then here it was 1/2 times 1/2, so 1/2 twice. And here it was 1/2 times 1/2 times 1/2, 1/2 3 times. Because it's just dependent on the number of offspring. And so we've already pretty much worked out that basically the probability of each line is equal to, well, we can write that as 1/2 to the power of something. Remember, the power of something just means 1/2 times 1/2 times 1/2. So in this case, we can do it to the power, so it's the number of offspring, right? Here it's 1 offspring, so 1 1/2. Here it's 2 offspring, so 2 1/2. And so we're using n to represent our number of offspring, and so we can just do 1/2 to the n. Okay, so we're kind of halfway there. We've got a probability per line, and now we need to figure out our number of lines. So let's figure out, we've done this for a couple of them so far. So so what we're looking at here is this is n, the number of offspring, and then this is for a given number of daughters. We're just going to put the number of lines that we have. So to start out with, when we had n equals 1, when we have 1 offspring, the probability we have 1 daughter, well, that's just given we only have 1 line. So that's actually 1 here, and the probability we have 1 daughter is also 1 line. For 2, we found that it went 1 line for 0 daughters, 2 lines for 1 daughter, and 1 line for 2 daughters. For 3, we get 1 3, 3, 1. Okay, so we see some patterns here, right? So first, if we have 0 daughters, well, how many different ways can we get 0 daughters? Well, there's only one. It's just if every offspring is a son. So son, or son, son, or son, 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 or son, 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 son. So there's only one way to get 0 daughters. And sort of similarly, if we look at the other end here, so this is one daughter out of one offspring, or 2 daughters out of 2 offspring. So these ones are also, those are the cases where you have daughter, or daughter, daughter, or daughter, 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 or daughter, 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 daughter. So we've got ones going down the left, and we've got ones on this diagonal. Okay, so we can also see that here we get 1, 2, 3. Well, so if we think about that, so this is for getting 1 daughter. Well, if we've only got 1 offspring, then we've only got one way to do that. The daughter has to be the 1 offspring. If we have 2 offspring, well, now we have 2 ways to do it. The daughter could be first, or the daughter could be second. So we have 2 ways if there's 2 offsprings. 2 ways to get 2 daughters if there's, 2 ways to get 1 daughter if there's 2 offspring. Okay, well, what about here? Well, now we could have the daughter be first, or the daughter be second, or the daughter be third. So if we have 3 ways if there are 3 offspring. So here with 4, we have the daughter could be first, or second, or third, or fourth, so there's 4 ways. And so this is going to be 1, 2, 3, 4. So we can start to fill this stuff in. So also 1 off this diagonal. So we said the diagonal is 1, 1, 1, 1, 1. So the next one over is the same thing. So this is where we have 1 son, this is where we have 1 son, this is where we have 1 son, and so forth. Because this is where D is n minus 1, right? So 1 offspring, 0 daughters, that's 1 son. This is 2 offspring, 1 daughter, that's 1 son. This is 3 offspring, 2 daughters, that's 1 son. So this diagonal is 1 son. Same way that we said, same thing as for daughters. If you have 1 son, then you have n ways to do that. And so we can start to fill some of this in. Sorry, we're starting to crash into our equation over here. Why don't I go ahead and rewrite that? Okay, so we're starting to fill this out, but we still have some missing bits here. So how many ways are there to get, if you have 4 offspring, how many different ways are there to get 2 daughters? Or if there are 5 offspring, how many ways are there to get 2 daughters? So the way I think about this is as follows. So my 2 fingers are going to be 2 offspring, 2 daughters. And let's say this one is called Anna and this one is called Beatrice. So we want to figure out how many ways do we have with our 2 different daughters, with our 2 different names, how many ways do we have that we can arrange them? Okay, so the way I think about it is we're going to take daughter number 1, Anna. So Anna can go in one of 4 positions. So let's say we choose the first offspring for Anna, then Beatrice can go in 3 different places. So we have 4 different places we can put Anna, and then we have 3 different places that we can put Beatrice. So it seems like the number of lines in this case is going to be something like 4 times 3. Right? Because we have 4 places to put Anna, and then we have 3 places left over to put Beatrice. So is that right? Well, if we look here with our 4, so these are our cases where we have 2 daughters out of 4, and we find that we have 6, not 12. So we're not quite there yet. Well, if we think about it, we've said that we've written down these 12 different possibilities, like Anna and then Beatrice, and then 2 sons, or Anna and then a son, and then Beatrice and then a son. So we have a bunch of these, but I just want to point out that some of these, so let's look at this one. So we have Beatrice and Anna, and then 2 sons, and Anna and Beatrice and 2 sons. Because that was when I put, right, in one case I put this, my left finger first, and then my right finger. In the other case, I put my right finger first and my left finger. So that means these 2 combinations, if we keep my fingers separate and give them different names, they're different ones. But they're both daughter, daughter, son, son. And so we have 12 combinations, but we're kind of double counting because we've counted this and that. So we need to divide this by something. So what do we need to divide it by? Well, in this case, there's 2 ways, because we only have 2 individuals, there's 2 ways that we can either go this way or this way. And so we're going to end up dividing it by 2. Okay, so we're getting close, and that does get us to 6. So that's how we can see our 6 combinations. Well, let's do one more. Let's do up to 5. Okay, so if we have 5, then we have our 5 boxes. So we have our 5 positions, our 5 offspring, 1, 2, 3, 4, 5. Okay, so we know how to do just one daughter. That's 1, 2, 3, 4, 5. So let's do 2 daughters. So it's similar to what we just did. So we have Anna and Beatrice, 1, 2, 3. So we have all these different combinations. But then, so we have 5 places to put Anna times 4 places to put Beatrice. And then we have to correct for the fact that we can get Anna and Beatrice in 2 different orders. And so for here, we get 5 times 4 divided by 2. Okay, so now let's move it up to 3. Okay, so now we have Anna, Beatrice, and Candace. So we have 5 places to put Anna, and then we have 4 places to put Beatrice, and we have 3 different places to put Candace. So we're going to start out with 5 times 4 times 3. But now we have to correct for the fact that we have all these different ways. So we need to figure out, so let's say that how many different ways, if we said that we have daughters in 1, 2, and 4, then how many different ways could we have gotten that? So we can write down those ways. So that would mean if these are the 3 places in our position where we have daughters, the first, second, and fourth, for instance, then we could have Anna, Beatrice, and Candace, or we could have Anna and then Candace and then Beatrice, or we could have Beatrice and then Anna and Candace, Beatrice, Candace, and Anna, Candace, Anna, Beatrice, and then Candace, Beatrice, and Anna. So we have 6 combinations. Let's figure out if we can work out how we got that 6. Well, one way to think about this is now among these 3, we have, if we're gonna basically randomly place A, B, and C, our 3 names, within our 3 daughters. And so for Anna, we have 3 places we can place her. And then once we've placed her, we have 2 places we can place Beatrice. And then we have 1 place left over that we can place Candace. And so that basically the number of different ways that we can have take our 3 names and get the same order of daughters, the same places of daughters. The number of different ways we can do it in each case is 6. So before, when we just had Anna and Beatrice, there were 2. Now when we have 3, there's 6. And we worked out that it's equal to 3 times 2 times 1. I'll blow this up in a second, so don't worry about it. Okay, so we're starting to get this. We've got 5 times 4 divided by 2, and then we've got 5 times 4 times 3 divided by 3 times 2 times 1. And I'm not going to show it here, but if we wrote down all the combinations, we would find out that yes, indeed, we get 10 of these, 5 times 4 divided by 2, and we get 10 of these, 5 times 4 times 3 divided by 3 times 2 times 1. Okay, so now we're kind of learning how we could work this out, but we'd like an equation that's a little bit easier to do so that we don't have to constantly be redoing this and doing it by hand. So let's give ourselves some workspace. Okay, so for our number of lines, well, let's do this example of that we just did, where we have 5 times 4 times 3 divided by 3 times 2 times 1. So we can see that these numbers, 5 times 4 times 3, it's kind of, there's this sequence of numbers starting at some number and then going down. We can use this thing called called factorial. So 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So then what we're seeing here, well, the first thing we see on the bottom, this is 3 times 2 times 1. So we can rewrite that as 3 factorial. And then on the top, we have 5 times 4 times 3. It's kind of like a factorial, but it's sort of lazy, right? 5 times 4 times 3, but it never got all the way there. So what are we missing here? Well, we're missing a 2 and a 1. None of it would be 5 factorial. So we just added this extra stuff. And to remind you, if we're dividing one thing by another thing, as long as we multiply the top and the bottom by the same thing, we're okay. So we just multiply the top by 2 times 1. And here I'm going to multiply the bottom by 2 times 1, and those cancel out. So this means this is still the same value. So this is a way that we can get back to a factorial on the top, so that now we can rewrite this thing as just 5 factorial. And notice we can write 2 times 1. Well, that's also can be written as a factorial. It's equal to 2 factorial. And so now we can start to rewrite this stuff. So we just said that we can rewrite 5 times 4 times 3 as 5 factorial divided by 3 factorial times 2 factorial. Well, let's look at this one. Well, this is 5 times 4. So we could do the same thing we just did, and we'd see that actually 5 times 4 is equal to 5 factorial. 5 factorial divided by 3 factorial. I'm just rewriting. So we've got our 2 and then our 3 factorial. Well, what about 2? Well, we can write 2 is equal to 2 times 1, because that 1, if you multiply by something by 1, it doesn't change it. So this 2, we can instead write 2 times 1, or 2 factorial. Okay, so we've got something, we've got a way to get some of these numbers, but we want a way that we can get all of these numbers. So let's think about 5. So, well, 5, it seems like a dumb way to write it, but stay with me. We can write 5, so we've got 5, and now what I'm going to do, I'm going to multiply the top and the bottom by 4 times, 3 times 2 times 1, or just by, we could just say, just by times 4 factorial. So now we got 5 times 4 factorial over 4 factorial. Well, this is just 5 factorial, because it's 5 times 4 times 3 times 2 times 1. And we get 5 factorial over 4 factorial. Okay, so we can rewrite this as 5 factorial over 4 factorial. So we start to see a pattern here, right? We've got 2 factorial, 3 factorial, 4 factorial. And we've got 3 factorial, 2 factorial, so it seems like we could put 1 factorial here. Well, okay, so we've just divided this by 1 factorial. Is that okay? Well, 1 factorial is just 1, and so we can divide a number by 1. It doesn't change anything. So that works. We can write 5 as 5 divided by 1 factorial, 4 factorial. And what about 1? Well, we can actually write 1 as 5 factorial divided by 5 factorial, because a number divided by itself is 1. And then, so this is a little bit weird. We're going to define 0 factorial as equal to 1. That basically, like, when you're doing a factorial, you start at 1, and then you multiply it by some stuff, 5, 4, 3, 2, 1. But if it's 0, you don't multiply it by anything. It's a little bit funny, but in general, 0 factorial is defined to equal 1. And so that means then we could stick a 0 factorial wherever we want. I can multiply, you can give me your money, and I'll give you back all your money times 0 factorial, same amount of money. Okay, and so now we can see a pattern. We've got basically 5 factorial divided by 0, 1, 2, 3, and 5 factorial divided by 5, 4, 3, 2. And so this one, so we can do the same thing we did over here, that we can recognize that 5 factorial is equal to 5 is equal to 5 factorial divided by 4 factorial, 1 factorial, and that 1 is equal to 5 factorial divided by 5 factorial, 0 factorial. Okay, so we've got a pattern here where it goes 0, 1, 2, 3, 4, 5, and in 5, 4, 3, 2, 1, with our factorials. So now we have an equation, we have an expression where we can get the number of lines given any n and d. And so what we see is, in each case, this is n factorial, it's 5, and we can sort of see here this is 4 factorial divided by 2 factorial, 2 factorial. So it's going to be the number of, it's going to be n. So it's n factorial divided by, well, what's 0? Well, it's the number of daughters. So the number of daughters, factorial. And then what's 5? Well, it's the number of sons, right? If you have 0 daughters and 5 offspring, then you have 5 daughters, 5 sons. If you have 1 daughter, you have 4 sons. If you have 2, you have 3 sons. Or if you flip a coin and you get 10 times and you get 3 heads, you have 7 tails. If you get 4 heads, you have 6 tails. And so it's just, the whole equation just simplifies to this. So we have n factorial divided by the number of daughters factorial times the number of sons factorial. Or if you want to ask the question, if I flip a coin 10 times, what's the chance I get 7 heads and 3 tails? Then it would be just 10 divided, or the number of flips factorial divided by the number of heads factorial times the number of tails factorial times 1/2 to the number of flips. Okay, so this is our binomial theorem. The probability that we get that something happens d times, that one thing happens d times and the other one happens s times, given that we have we have n different trials, flips or offspring or whatever, can just be given by this equation. 1/2 to the n times n factorial divided by d factorial s factorial. And this is known as the binomial distribution or the binomial theorem.